In this video, we're going to go over some practice problems from the end of chapter 5 and the beginning of chapter 6 of our textbook. So starting with section 5.5 here, we want to solve equations using what's called the zero factor property. Now the zero factor property says the following. If we have the product of two things, we're going to call A and B. And if this product gives me 0, then this means either A is going to be equal to 0 or B is going to be equal to 0, or we could have that both of these factors are equal to 0. Okay, if A is equal to 0, then this would be a true statement if we were to plug 0 back into this, and similarly for B. So with this in mind, we're going to solve the following four equations. Looking at this first one here, notice we have the product of two factors equaling 0. So right off the bat, we know that we can use our zero factor property because it's in this form. We have the product of two things giving me 0. So applying the zero factor property, this tells me that either my first factor is going to be equal to 0, or my second factor is going to be equal to 0, or both of these could be equal to 0. So what we need to do is then solve both of these equations for k, and these would be our two potential solutions that will make this statement true. So let's go ahead and solve for k for this first equation here. We're going to subtract 8 on both sides of our equation. We're going to get 3k is equal to negative 8. Then to completely isolate k, we're going to divide both sides by 3. We're going to end up with negative 8 over 3. So this would be our first solution, or our first potential solution. Doing the same thing to our other equation here, we again want to solve for this variable k. We're going to start off with adding 5 to both sides of our equation. We're going to get that 2k is equal to 5. And lastly, to completely isolate our variable, we're going to divide 5 by 2. We're going to divide both sides of our equation by 2. Now, I'm saying that these are two potential solutions because it could be the case that one of these is not satisfied or one of these does not make the statement true. Now, in all of the examples that we're going to see in section 5.5 in this video, all of these solutions will be solutions. So in the interest of time, I'm not going to check them, but I do encourage you to check them. Make sure that when you plug in these values into our original equation, you do get a true statement. So you should be able to plug in negative 8/3 into k and get 0 here. You should be able to plug in 5 over 2 into k and also get 0 here. Okay, so make sure to check that. We're going to write our answers as a solution set here. So our solution set is going to be negative 8 over 3 and positive 5 over 2. All right, so that's how we'd solve that one. Let's look at this next one here. Let's look at 21. Now, again, we want to solve this equation. And so far, we only know how to solve these equations, linear equations, where we would isolate one variable. But in this case, we're dealing with a quadratic equation because we have this degree 2 here. So the only way we know how to solve a quadratic equation so far is to use our zero factor property. So what we need to do first is make sure that it's in this form where we have the product of two things equaling 0. So far, we do have 0 on the right-hand side, so one of these steps are satisfied, or one of these conditions is satisfied. But we need to rewrite this so that we have the product of two things equaling 0. Right now, we have the sum of two things equaling 0. So what we can do is factor this. Now notice, this is not a trinomial here, so our factoring process is not going to end up with the product of two different binomials, meaning our factored form is not going to look like this. It's not going to look like the product of two binomials here since we don't have a trinomial. So instead, what we're going to do is see if we can pull out a common factor from both of these terms. Now notice both of these terms has a factor of 6x. So what we're going to do is pull 6x out from both of these terms. If I pull 6x out from this, I'm just going to be left with 1x. And if I pull a 6x out from the second term here, I'm just going to be left with 6. Okay, so we're going to end up with this equation here. So what we did, we pulled out this greatest common factor of 6x from both of these terms. Now we always want to double check and make sure that our factored form does end up being our original equation here. So what I mean is we want to make sure that if we distribute the 6x to both terms in our parentheses, we end up with the original equation that we started with. And distributing this, we'll see that that is the case. So this tells us that this is the factored form of my quadratic equation here. Now what I want to do is apply our zero factor property. Notice we have the product of two things, 6x and x plus 6, and this product gives me 0. So the zero factor property then says 6x must be equal to 0, or our other factor, x plus 6, must be equal to 0. So we're going to solve for x for both of these equations. In this case, I want to completely isolate x here, so I'm going to undo this multiplication by 6 by dividing both sides by 6 here. Now 0 divided by 6 is just going to give me 0. So I'm dividing by 6 on both sides. So x is going to be equal to 0. That's one potential solution. Or on the other hand here, I'm going to subtract 6 on both sides of my equation to completely isolate x. I'm going to get that x is equal to -6. And again, I do want to make sure that these are in fact solutions. So we should check them by plugging these potential solutions back into our original equation. But I will tell you now that these guys are both solutions. So our solution set is going to be -6, comma 0. Now, something to note about this type of equation here, this is a quadratic equation that's missing its constant term, right? We don't have that constant term at the end of this equation here. So in this instance, most of our equations will look like this in their fully factored form. However, if on the other hand, we are missing our linear term, this would look slightly different. Now, something to note here is that this 6 being attached to this variable indicates that it will give or it will provide a solution. However, if we just had a 6 on the outside, let's say there was no variable attached to this factor, then it wouldn't influence our solution. So just keep that in mind here. If this were just a number by itself, we would only be focusing on the factor that contains a variable. All right, let's look at this next example here. So in this instance, we again want to solve this equation for our variable x. And what we need to do first is we need to expand both sides of our equation and then combine like terms. We want to simplify this equation as much as possible before we start applying our methods for solving for these variables. So what I'm going to do here is FOIL everything on the left-hand side of my equation. So we're going to multiply these guys, these guys, and these. On the left-hand side of my equation, then, I'm going to end up with 2x squared. This would be my first term by multiplying these guys. So automatically, I know that I'm going to have a degree 2 term, so I'm most likely going to end up with a quadratic equation of some form. So this tells me I will probably have to factor and use my zero factor property. But let's continue on with the rest of the simplification here. 2x is going to multiply -3, so that's going to give me a -6x. Then I'm going to have positive x and then -3. So plus x minus 3. Then on the right-hand side, I have 6x plus 3. So now, like I said, we want to simplify by combining like terms. So what I'm going to do is I'm going to move everything on the right-hand side of my equation, all of these, to this side here. Now we want to do that because remember, on the right-hand side of our equation, we do want to get that this is equal to 0 if we want to use our zero factor property. So I'm going to subtract 6x on both sides. And in the same step here, I'm going to minus 3. Now we have to be careful with our signs here because these guys are going to cancel here because we have a positive 6x and a minus 6x and a positive 3 and a minus 3. So on the right-hand side of our equation, we should have 0. But here we have a minus 6x and a minus 6x. That would give us minus 12x. So we're going to have 2x squared, and we have a minus 12x here, but then we have a plus x. So this would give me minus 11x. And then here I have a minus 3 and a minus 3. So that's going to give me a minus 6. And then we have 0 on the right-hand side of our equation. So now notice we have a trinomial. So what we need to do is factor this, get it into this form here, where we have the product of two things equaling 0, and then apply our zero factor property. So let's go ahead and factor this. We know that our first term needs to give us a 2x squared, or the product of our first two terms needs to give us a 2x squared. So we're going to have a 2x and an x here. We know that this is going to be the first step in our foiling process. We're going to multiply the first terms, and that'll give us this leading term here, which is 2x squared. Now, the second condition we need is that the product of these values is going to give us a -6. So there's a couple different combinations. We could use a -3 and a +2. We could use a +1, a -6, and so on. And we can keep switching those signs and guessing and checking until we get the right combination. But something to note here is that this 2 is going to multiply this as well. So it's going to increase this magnitude. That's why we have to be careful of this coefficient here. I also need my middle term to be a -11x. So if I were to use, let's say, a 6 here, notice when I multiply this, that's going to give me a 12x. Then when I multiply these guys, that's going to add to whatever our middle term is. So I kind of have an idea that maybe I should have a 6 here and a 1 here. Okay? If I multiply this, I'm going to get 12x if this was a positive guy. And then if this was positive, I would end up with a 13x because we're going to combine the like terms in the middle. So I'm kind of just thinking out loud what the signs are going to be for this example. And I'm ultimately going to choose a -6 and a +1. So when I FOIL this, I'm going to get 2x squared minus 12x and then plus 1x. That'll give me my middle value of 11x. Then my last step here in the FOILing process is 1 times -6. That would give me a -6. So this tells me this is the correct factored form of this guy. So now I have the product of two things equaling 0. So I can use my zero factor property. So 2x plus 1, that first factor, is going to be equal to 0, or my second factor is going to be equal to 0, and then I can solve for my variable x. I'm going to end up with 2x is equal to -1 here, and then dividing by 2, I'm going to get x is equal to -1/2. Doing the same thing for my second equation here, I'm going to end up with x is equal to +6 by adding 6 to both sides of my equation. So my final answer is going to be -1/2 and 6. This is the set of solutions for our original equation. And as usual, we should always check these values to make sure that we end up with a true statement when we plug in these solutions into our variable. Now for this next example, we again want to solve for our variable x, and we know how to do that by factoring these quadratic equations and using our zero factor property. Now notice we have one of our requirements for the zero factor property. We have 0 on one side of our equation. So maybe we want to rewrite this so that we get the product of 2 or maybe even 3 factors equaling 0. Now in this case, we're dealing with a third degree trinomial. So we're not entirely sure how to factor this yet. We've been mostly dealing with second degree trinomials. But notice we have a common factor for all of these terms here. Each term shares a factor of x. So what we can do is we can pull out that factor of x, and we're going to be left with a second degree trinomial in our parentheses here. Now this becomes much easier to factor. We know that our first term needs to be 2x squared. So we know we're going to end up with a 2x and an x here, the first terms in our two factors, and this is equaling 0. Okay, so that's the first requirement. Our first step in the FOIL process is going to give us this. Now we also know that the product of these two values needs to give us a -5. Now the only two options for this would either be -1 and +5 or the other way around. So if we go ahead and do that, let's do -1 and +5 and see what we get when we FOIL this. We want to get 2x squared plus 10x minus x and then -5. That's going to give me a +9x here. That's not what we want. We need a -9x. So this tells me that we can probably achieve that by switching the signs of these guys. Let's go ahead and FOIL this. I'm going to get 2x squared minus 10x plus 9x minus 5. So that gives us the desired middle term. So this tells us this is the factored form of this guy in our parentheses here. So now we can use our zero factor property. Notice in this case, though, we have 3 factors. We have the product of 1, 2, 3 factors equals 0. Well, the zero factor property still applies. If this is 0, then this entire statement is true, or if this is 0, or if this is 0. So what we're going to have here is one of our solutions is that x is going to be 0. Plugging 0 into this guy gives us 0 for this whole thing. We're also going to have our first or our second factor in this case equaling 0, or our last factor equaling 0. And again, we proceed as normal. For this one, x is equal to 0. We don't have to do anything here. Let's look at our next equation. If we want to solve for x, we are going to subtract 1 on both sides and then divide by 2. So we're going to get x is equal to -1/2. And then lastly, we're going to add 5 to both sides for this equation. So we're going to get that x is equal to +5. So our solution set is then going to consist of 3 solutions. We're going to have -1/2, 0, and 5. Now, in this case, remember we were dealing with a third degree trinomial. So this is kind of an indication that we're going to end up with 3 solutions and we're dealing with a third degree equation. And per usual, don't forget to check that these solutions satisfy. Now, for this next example, we're looking at an applied problem. So we're told that if an object is projected upward with an initial velocity of 64 feet per second from a height of 80 feet, then its height in feet t seconds after it's projected is modeled by this function here. So this would be a quadratic function. Now what we want to figure out is after how many seconds will the object be 128 feet above the ground? Well, remember this function that we were given is the model for our height. So this tells us that f of t is going to be our height of this projectile t seconds after it leaves the ground. So in this instance, 128 feet is going to be our value for f of t. So what we can do then is we can plug this value for f of t into our function and solve for t. The question asks for after how many seconds will this object be this high off the ground. So we'll plug in this information to this guy and solve for those seconds. So let's go ahead and do that here. We're going to have 128 feet is equal to our function. So negative 16t squared plus 64t plus 80. Let's move this up a little bit. We might need some more room. All right. So again, we're dealing with a quadratic equation. So we know how to solve this by factoring and then using our zero factor property. Well, before we do that, we need to make sure that we have the quadratic equation in standard form. So we need 0 on this side of our equation. So what we'll do is we'll subtract 128 on both sides. We're going to get negative 16t squared plus 64t minus 48 is equal to 0. All right, now what we can do is factor this. But remember, we usually don't like our second degree term to be negative here. We try to avoid that as much as possible by pulling out a negative. It's just going to help us when we're factoring this. Also, before we factor this into the product of two binomials, we want to make sure that we can pull out a greatest common factor. Now notice each of these terms has a greatest common factor of 16. So if I were to pull that common factor out, I'm going to end up with a quadratic equation that's much simpler to deal with. Now, in order to do that, what I'm going to do is I'm going to divide both sides of this equation by 16, by that common factor. But remember I said we don't want this first term here to be negative. So what we're going to do is we're going to take that negative out by dividing by a negative on both sides of our equation. So what we're left with here, our first term, we have negative 16 squared divided by negative 16. So we're just going to be left with positive t squared. Then we have 64t divided by negative 16. This is going to change our sign. We're going to end up with a minus 4t. And then lastly, we have a negative 48 divided by a negative 16. That's going to make our value positive, and it'll be a positive 3. Now on the right-hand side here, we have 0 divided by negative 16. Well, 0 divided by anything is just going to give us 0. So we ended up with a much nicer trinomial to work with instead of this one here. So now what we can do is factor this trinomial. So let's go ahead and do this over here. Now this one's a little bit simpler than what we saw in the last several examples because the coefficient of our second degree term here is 1. So we know that our first two terms for each of our binomials is going to be t. We know that our first step in the FOILing process needs to give us t squared. We also know we need to find two values whose product is going to be 3. And since the coefficient of this first degree term here is 1, we also need those same numbers to add up to give us a negative 4. So these two values would be a minus 1 and a minus 3. The product of negative 1 and negative 3 gives us a positive 3. And if we were to add these guys together, we'd get a negative 4. We can, of course, check our answer by FOILing and making sure we end up with this original trinomial. Now, don't forget, this is all equal to 0. So now we have the product of two things equals 0. We can use our zero factor property. This says t minus 1 is equal to 0, or t minus 3 is equal to 0. Solving for our variables for both of these equations, we're going to get t is equal to 1 or t is equal to 3. So what this means is the object will be 128 feet above the ground after 1 second and again after 3. So we'll say after 1 second and again after 3 seconds, because the question is asking how long will this happen. Now, this makes sense in the context of this problem. If we were to think about this visually, let's say this here is going to be our height, and this here is our time in seconds. So if we were to shoot this projectile from the ground, let's say this height here is 128, it's going to have a path like this. Due to gravity, it's going to look like a parabola. So this means our object's going to hit a height of 128 feet twice, there and there. So this first instance would be 1 second after it left the ground. And this one here would be about 30 seconds after it left the ground. All right. Now for part B, how long after it is projected will it hit the ground? So in this case, when it hits the ground, the height is going to be 0 feet. So now we're going to do the same thing here, except our height now is going to be 0 instead of 128. So we're going to have a similar process. We're going to start with our quadratic function that we were given. And our height is going to be equal to 0. And sorry, our original function was actually a plus 80 here. All right. So now what we need to do is solve for t. The question asks how long after it is projected will it hit the ground? So again, by the same reasoning that we saw in part A here, we're going to divide both sides of this equation by -16 to simplify this trinomial. We're going to end up with a trinomial that looks like this. We're going to have t squared minus 4t minus 5 is equal to 0. Now again, we want to factor this and use our zero factor property. So we know we're going to have a t and a t here. And we know we need to find two numbers whose product is -5 and whose sum is -4. This would be a +1 and a -5. -5 times +1 gives us a -5. And if we were to add these values together, we get a -4. But of course, we can FOIL this to make sure we end up with our original trinomial. Now what we're going to do is use our zero factor property. So this tells us t is going to be equal to -1 or t is going to be equal to +5. Now, something to note about this problem is that we have to think of our solutions in the context of the problem that we're dealing with. We're dealing with t as in seconds, and in this case, we got t is equal to -1. So we would actually disregard this solution because we can't have negative time. That doesn't make sense in the context of this problem. So our only solution would be this guy here. This t is equal to 5. So this means the object will hit the ground 5 seconds after it's thrown. So object will hit the ground after 5 seconds. This brings us to our next section where we're looking at writing rational expressions in their lowest terms and multiplying or dividing rational expressions. So for the first three questions here, we want to write each rational expression in its lowest terms and give the domain. So for this first one here, what we want to do is simplify this. We want to figure out if there's anything in the numerator that can cancel with anything in the denominator, and we can do so by factoring. So that's our first step here whenever we want to write our rational expressions in our lowest terms. So let's go ahead and factor the numerator. Both of these terms have a common factor of z. So I'm going to go ahead and pull that out and see what we're left with. So that's our numerator. Let's do the same thing in our denominator. Both of these terms share a common factor of 6, so I go ahead and pull that out. Pulling out a 6, I'm going to end up with 3z plus 1. Now notice I have a 3z plus 1 in the numerator and in the denominator, so these guys cancel. My final answer is going to be z over 6. This is going to be our rational expression in its lowest terms. Now we also want to give the domain of this. So this is going to be anything that makes our denominator 0. We need to figure out what values will make our denominator 0 and exclude them from our domain. Now at first you might think the domain will be all real numbers because the 6 here will never be equal to 0. However, when we're looking at these rational expressions, we need to look at our original denominator in order to find our domain. So instead of saying all real numbers here, we need to go back to our original denominator and figure out what values of z will make this equal to 0. So we're going to set our denominator equal to 0 and solve for z. I'm going to subtract 6 on both sides. So I'm going to get 18z is equal to -6, and then I'm going to divide by 18. Now, 6 and 18 both share factors of 6. So z is going to be -1/3. So this is the value that we need to exclude from our domain, because if z is equal to -1/3, then our denominator is going to be 0. And remember, we can never divide by 0. So our domain in this case, we'll write it in interval notation, is going to be from -infinity up to -1/3, but we're not including this value. We're saying everything up to this value and not including it, and we're indicating that with a parenthesis. If we were including this value in our domain, we would have had a bracket here. We're going to union this with everything in the other direction. So from -1/3 all the way up to +infinity. And again, we're not including this 1/3. So we have this gap here where -1/3 is. All right, let's do the same thing for the next two examples. We again want to write both of these guys in their simplest terms or their lowest terms. And the first step in order to figure that out is to factor both the numerator and the denominator and see what we can cancel. Factoring this, we know we're going to have x and x for our first two terms in each of our binomials. Then our last two terms need to multiply to give us a -15 and add to give us a +2. Those two values are going to end up being -3 and +5. And we always want to FOIL and make sure that we end up with the original trinomial that we started with. Doing the same thing in the numerator here, we know that our first two values in our binomials are going to be x. Then we know that these guys here need to multiply to give us 5 and add to give us 6. Well, this one's fairly simple since we have a +5 and a +6. Now notice we have an x plus 5 in the numerator and in the denominator, so these guys cancel. And in lowest terms here, this is going to be x minus 3 over x plus 1. But again, we want to find the domain. And like we saw in the last example, we might want to just look at this as denominator, but we actually need to look at our original denominator here. We need to figure out what values of x will make this guy 0. And in this case, we're going to have two different options. We have x plus 1 times x minus 5. This is our original denominator, and this is equal to 0. So we can use our zero factor property to see what values of x will make this statement true. So we're going to end up with x is equal to -1 or x is equal to +5. So these are the values that we are going to exclude from our domain. So our domain for this guy in interval notation is going to be -infinity all the way up to -1, but not including -1. -1 up to 5, but not including either of those, and then 5 up to infinity. So we're saying everything up to -1, everything in between these guys, and then everything past. All right, let's do the same thing for this last one. Now, we want to, again, write this in its simplest or lowest terms. We want to figure out if we can cancel anything in the numerator and the denominator. But notice this is already in factored form, and none of these guys share a common factor here. But looking at this 8 minus p and this p minus 8, notice that these are exact opposites of each other. So what I mean is, we could factor out a negative from one of them and end up with the same factor. So let's factor out a negative from the numerator. If I pull out a negative from this guy, it's going to change both of these signs. I'm going to end up with a -8 and a +p. Let's write out the rest of our expression. All right, now let's rewrite this. -8 plus p is the same thing as +p minus 8. So we're going to have +p minus 8 times x plus 2 in the numerator, and our denominator is the same. Now, notice we have, so this factor here turned into this factor, and now we have this p minus 8 in the numerator and in the denominator, so we can cancel them. Doing so, we're still going to have this negative out in front, but we're going to have x minus 2 over, or sorry, this should be x plus 2 in the numerator over x minus 2. And this would be our final answer. We can't simplify this any further. We could, if we wanted, we could distribute this negative to both terms here. So in the numerator, we would get a -x minus 2 if we wanted to do that. All right, now we again need to find the domain. So we're going to look at our original denominator here. We need to figure out what values are going to make this guy 0. And using our zero factor property, we can easily see that p minus 8 is going to be equal to 0 or x minus 2 is equal to 0, and we can solve for those variables. So we're going to have p minus 8 times x minus 2 is equal to 0. So p equaling positive 8 or x equaling positive 2 would make our denominator 0. But notice that we're dealing with two different variables. We have a p and an x here. So what we're going to do is kind of split this up into two cases. So the function is going to be undefined when p is equal to 8, no matter what. That would make our denominator 0. That would make this factor 0, and 0 times anything is 0. Now, the function is also going to be undefined when x is equal to 2 for the same reasoning. This would make this 0, and 0 times anything is 0. So we're going to split our domain up into two cases. In terms of x here, we're going to look at the case when p is equal to 8. Our function is going to be undefined for all x. So we'll say undefined for any x value. And our second case is when p is not equal to 8. If this is the case, then our function is undefined for x is equal to 2. And we're not going to go too in depth about this. We're not super concerned about the domain in this case. I just wanted to explain that this is kind of what we do if we have two different variables. For this problem here, we're mostly concerned about writing this in lowest terms. Now, the last three examples in this section, we're going to be multiplying or dividing rational expressions. Now, two things to note here is that whenever we're multiplying rational expressions or rational numbers for that matter, we're multiplying straight across. So this 4x is multiplying this whole thing, and this whole thing is multiplying this 6. So what we can do is just go ahead and multiply straight across, but we want to also write our final answer in lowest terms. So what we can do at the same time is also factor every single term in our numerator and our denominator. So what I mean is when we want to multiply these rational expressions, the first step would be to factor them. So 4x for our first expression here can't be factored any further, so we'll leave that as it is. But 8x plus 4 can be factored because 8x and 4 both share a factor of 4. So pulling that out, we're going to be left with 2x plus 1. So this would be our first rational expression fully factored. Let's do the same thing with this second one. 14 and 7 both share a factor of 7, so we can pull that out. We're left with 2x plus 1, and in our denominator, we're just going to have that 6. All right, now let's go ahead and multiply straight across. So 4x is multiplying 7 times 2x plus 1, and then everything in our denominator here is multiplying 6. Now that we have everything in factored form and multiplied straight across, we can easily see that some things are going to cancel. We have a 2 plus x in the numerator and the denominator, so these guys can cancel. And then we also have a 4 in the numerator and a 4 in the denominator. So this simplifies to, we're going to have 7x in our numerator, because we still have this 7 and this x here. And in our denominator, we're just going to be left with this 6. And this would be our final answer. This is the product of our two rational expressions in its lowest terms. All right, let's do the same thing for the next two examples. We want to multiply these guys and write them in lowest terms, and we can do that by factoring. Now for this next one here, though, we have an extra step. Notice in this case, we're dividing these two rational expressions. So in order to do that, what we're going to have to do is multiply by the reciprocal. So dividing rational expressions or rational numbers, we do this by multiplying by the reciprocal. So let's write it on the side here. If I had a over b divided by c over d, this is the same thing as taking our first expression multiplied by the reciprocal of our second. So that's what we're going to do here for question 79. We're going to take this first rational expression and multiply by the reciprocal of our second. So now that we've done that, we now have a multiplication problem, and we can proceed just like we saw in question 71 here. What we're going to do is factor both of these and multiply straight across and see if we can cancel anything. So in this first guy here, 4 and 20 both share a common factor of 4. So we'll go ahead and pull that out. I'm going to be left with x minus 5 in the numerator, and in the denominator, I'm going to have 5x. Doing the same thing for our second expression here, we're still going to have 7x cubed here, but 2 and 10 in our denominator share a factor of 2. All right, now we'll go ahead and multiply straight across. If we go ahead and do that, we're going to end up with this whole thing multiplied this whole thing, and this whole thing multiplying this. So we're going to end up with an x minus 5 in the numerator and the denominator. So instead of writing that step out like how we did in this first example, we can go ahead and just cancel them right away. We have an x minus 5 in the numerator and the denominator. Okay, so that makes everything much simpler. We're going to have 4 over 5x as our first term, and then we're going to have 7x cubed over 2 for our second. All right, so now let's multiply straight across and see what we can cancel. Notice we're going to have 4 times 7x cubed over, we have a 5x times 2. I'm going to go ahead and write that as 10x. Now what we can do is simplify. I have x cubed in the numerator and x by itself in the denominator. So I'm going to end up with an x squared in the numerator using our exponent rules. We also have a 4 times 7, so I'm going to end up with 28 x squared divided by 10. All right, now lastly, we again want to write this in our lowest terms here, and 28 and 10 both share a common factor of 2. So dividing both of these guys by 2, I'm going to end up with, we're going to have 14x squared in the numerator and 5 in the denominator, and that would be our final answer. Okay. Now, something to note here is I'm just writing out each of these steps one by one, but we could have also recognized that we have 3x's in the numerator here and 1x here. We could have canceled them in this step as well. We could also recognize that we have a 4 in the numerator and a 2 in the denominator, so we can take out a factor of 2 here. So whichever way you want to approach it, but if you do write it out step by step here, it does help you to kind of follow the process and catch any mistakes as you move through the problem. All right, let's look at this last example. We're again going to be multiplying two rational expressions. So the first thing that we want to do is factor them. So let's factor this first rational expression. In our numerator, we have a difference of 2 squares. So this is going to end up being t minus 7 times t plus 7. And this is solely because we have a difference of squares. T squared is a perfect square and 49 is a perfect square. In our numerator here, we know we're going to have a t and a t. We need to get a t squared as our first term. And we need two values that are going to multiply to give us negative 21 and add to give us a positive 4. This would be a positive 7 and a minus 3. So this is our first rational expression fully factored. Let's do the same thing for our second one. Factoring this numerator, we're going to end up with t plus 5 times t plus 3, two numbers that multiply to give us positive 15 and add to give us a positive 8. And in the denominator, we need two numbers that multiply to give us a negative 35 and add to give us a negative 2. So this would be t minus 7 times t plus 5. All right, so now we can go ahead and start canceling things. Notice we have a t plus 7 in the numerator and the denominator of our first expression. And we also have a t plus 5 in the numerator and denominator of our second. So let's go ahead and see what we have left. We're going to have a t minus 7 in the numerator and a t minus 3 in the denominator times t plus 3 over t minus 7. Now, again, we're going to be multiplying straight across when we multiply these expressions. So we're going to end up with a t minus 7 in the numerator and in the denominator here. So we can go ahead and cancel this right away. Multiplying straight across now, we're going to end up with a t plus 3 over a t minus 3. This is because when we cancel these guys here, we're going to be left with a 1 here. We're going to end up with 1 times t plus 3, which gives us t plus 3, and then t minus 3 times 1, which gives us that t minus 3. Now, in this last section in this video, we're going to be adding and subtracting rational expressions. Now, this process is similar to adding and subtracting rational numbers in that we need a common denominator in order to do so. So if we look at this first question, we want to subtract these two rational expressions. Now notice the denominator of both of these are the same. So we don't have to do anything here. We can go ahead and subtract straight across, leaving this denominator as is. And this is because we are subtracting them. If we were multiplying these guys, we would multiply these denominators together. So subtracting straight across, we're going to get y squared minus 36. So this is going to be y squared minus 36 in our numerator. And again, in our denominator, we're just going to have that common denominator of y plus 6. Now, this isn't going to be our final answer, though, because we again want to make sure all of our final answers are in lowest terms when we're dealing with these rational expressions. And notice in this numerator here, we have a difference of squares. This is y squared, which is a perfect square, minus 36, which is 6 squared. So we're going to rewrite this in factored form as y plus 6 times y minus 6. That's what our numerator becomes if we factor it. And then we have this y plus 6 in the denominator. Now, since we have both of these guys in the numerator and the denominator, they're going to cancel, and we're going to end up with y minus 6 as our final answer. All right, so that one wasn't too bad since we had a common denominator. But what about when we don't have a common denominator? If we look at this example here, we're subtracting these two rational expressions. This denominator is different from this one. So in order to subtract these guys, we need to get a common denominator. We can do so by multiplying one or both of these expressions by something that'll give us the LCD. Now, the LCD is the least common denominator, and it's going to be the product of all of the different factors from each denominator, with each factor raised to its biggest power. So we'll start by splitting up each of these denominators into their own factors. So looking at this first one, the factors of this denominator is 18, a cubed, and b squared. Now the factors of this guy is going to be 9 and a and b. So the first thing that we'll look at is this numerical factor. And again, we need to take the factor raised to the greatest power. So in terms of our numerical factor, we're going to take the biggest value. So in this case, that would be 18. So for our LCD, the greatest numerical factor that we're going to take is 18. All right, let's look at our next factor. We have an a cubed and an a, and we need to look at the greatest power that occurs. So in that case, this would be this a cubed. So this would be part of our LCD. Doing the same thing for this next factor here. We have this b and a b squared. Now, again, we're going to take the factor raised to the greatest power as our LCD. So in this case, that would be b squared. So now what we need to do is we need to multiply this second expression by something so that we get an 18a cubed b squared in our denominator. Now, something else to keep in mind here, just like we saw when we add or subtract rational numbers, whatever we do to the denominator, we also have to do to the numerator in order to not change this value or the value of this expression. So we're going to multiply the numerator and the denominator by something to get our LCD that we found. Now in this case, that's going to be a 2 because 9 times 2 is going to give us 18. Then we need two more factors of a, so that's going to be a squared, and one more factor of b, so that'll be a b. And again, whatever we do to the numerator, we're going to do to the denominator. Okay. So we're still going to have this first expression. We're going to have 7 over our LCD, and we're going to subtract out this new expression. So we're going to have 2 times this guy. We're going to end up with 4a squared b in our numerator, and our denominator, we're going to end up with that LCD that we wanted. All right, so now that we have a common denominator for both of these expressions, we can go ahead and subtract straight across. We're going to have 7 minus 4a squared b over our LCD. Now, notice we can't simplify this any further. We can't factor anything out or cancel. So this would just be our final answer. Now, for this next example, we're again going to be subtracting rational expressions, but now we're subtracting 3 rational expressions. So this might make our least common denominator a bit bigger. Now, again, our least common denominator is going to be the product of all of the different denominators in our rational expressions. And it's going to be each factor raised to its greatest power. So this would be one factor, this would be another, and this might be another. But notice that both of these denominators can't be factored any further. They can't be simplified, but this guy can. This is going to be a difference of two squares. X squared is a perfect square and 1 is a perfect square. So since this is a difference of squares, we should factor this. See if it has any common factors with any of these denominators here. Because remember, we're taking the factor raised to the greatest power. So let's go ahead and rewrite this expression. In our denominator here, since this is a difference of squares, we're going to have x plus 1 times x minus 1. All right, so now we have a better idea of what these denominators look like. And again, we're going to take the product of all the different denominators raised to the biggest power. So we have 1x minus 1, 1x plus 1, and then this denominator here has both of those factors, x plus 1 and x minus 1. So this would be our least common denominator. What we need to do is we need to multiply both of these expressions by something so that we get this denominator. So our LCD is going to be x plus 1 times x minus 1. All right, so we'll go ahead and do that. We're going to multiply each of these expressions here by something so that we get this LCD. So for this first one here, notice we already have one of the factors. We already have x minus 1. So this tells me all we need to do is multiply by the other factor, x plus 1. All right. Now the second expression is similar. We already have one of the factors, that would be x plus 1. So now we need to multiply by the other factor, the missing factor of x minus 1. And then we also have our last expression here, which already contains our LCD. All right. Now we're going to simplify this. We're going to have 4x times x plus 1 in our numerator. And in our denominator, we're going to have the LCD. Similarly, we're going to have 2 times x minus 1 here, and then our LCD here, and then we have our last expression. So now that we have a common denominator for each of these rational expressions, we can go ahead and subtract. Now, let's do that in this next step. We're not going to distribute or simplify anything. Let's just go ahead and subtract all of these guys since we have a common denominator. And we're going to do it this way instead of distributing or simplifying any of this stuff in the numerator first. And it's because of this minus sign. Now, this minus sign is being applied to both of these guys. So it's just kind of easier to see if we lay out this entire subtraction here in the numerator and then simplify it. So we have this entire subtraction here straight across, and we can do that again because each of these denominators are the same. Now let's go ahead and distribute and simplify and combine like terms. So we know that this 4x here is going to be distributed to everything in our parentheses, and we know this minus 2 is also going to be distributed to everything. We can't forget to take this minus sign with us. So we're going to end up with a 4x squared plus 4x minus 2x plus 2 minus 4 in the numerator. We still have our LCD in the denominator. Right? So now we can combine some like terms. We have a 4x and a minus 2x, and we also have a 2 and a minus 4. So we're still going to have 4x squared, then we're going to have plus 2x minus 2 in our numerator, and then this LCD in our denominator. Now, again, whenever we're dealing with these rational expressions, we do want to make sure that we simplify completely and write everything in its lowest terms. Now, notice our numerator here, this can be factored. We have a common factor of 2 in each of these terms, so that's the first thing I'm going to do. I'm going to pull that 2 out. I'm going to end up with 2x squared plus x minus 1 in my numerator. And again, I end up with a trinomial in our parentheses here that looks like it might be able to be factored. So we'll go ahead and do that here. We're going to have this 2 on this outside, and we know that our first two values is going to be 2x and x, so we can get that 2x squared. Now we need two numbers that are going to be multiplied to give us a -1 and add to give us a +1. So those two values are going to be -1 and +1. Now we still have our LCD here, so x minus 1 times x plus 1. Let me add a page here. I don't know if you can see the very bottom. All right, so we pulled out the common factor of 2 here, then we were left with this trinomial, and now we factored this trinomial. Okay. Now the next thing that we want to do is see if we can simplify this. And notice we have an x plus 1 and an x plus 1 here. So these guys can cancel. And our final answer in lowest terms is going to be 2 times 2x minus 1 over x minus 1. And this would be our final answer that we get after subtracting these three rational expressions. Now for this next example, we are adding these two rational expressions. Now in order to add these guys, just like we saw in the last several examples, they need to have the same denominator. Now, our LCD, again, is going to be the product of all of the different factors from each denominator. And notice that we have a trinomial in each of these denominators here. They're not in fully factored form. So we can't just look at these guys and easily know what the LCD is. So in order to determine the LCD, our first step is going to be to factor these trinomials. So we'll go ahead and do that. For this first expression here, we know that in our factored form, our first term needs to be m squared. So we're going to have an m and an m here. Now, these two numbers here need to multiply to give us a positive 4 and add to give us a negative 4. So those two values is going to be m minus 2 and n minus 2. Let's do the same thing for this second expression here. We're going to factor this, and we're going to end up with m plus 3 times n minus 2. Foiling this, we're going to get m squared. Distributing this and this guy gives us a positive m, and then 3 times negative 2 gives us a negative 6. So we've rewritten these guys in their fully factored form. Now we can see what the LCD is. Remember, it's going to be the product of all of these different factors, with each factor raised to its greatest power. So we're going to see that in this case. Notice we have an n minus 2 twice and an n minus 2 once here. So this means for our LCD, we're going to take n minus 2 twice, since we're looking at the factor raised to its greatest power. So we know we're going to have m minus 2 twice. And looking at the second denominator here, we're also going to take this m plus 3. So again, just emphasizing that the LCD is going to be each factor raised to its greatest power. That's why we have two of these. The second denominator does have a factor of n minus 1 or n minus 2, but we only have one of them. So that's why we take these guys. Now, something else to note here is that n minus 2 times n minus 2 is also n minus 2 squared. So that's how I'm going to write it moving forward. So the LCD then is n minus 2 squared times m plus 3. So what we need to do is we need to multiply both of these by something in order to get this LCD. So notice for this first expression, we already have the two factors of n minus 2. So what we need to do then is multiply the numerator and the denominator by this guy to get the entire LCD. So we're going to have m minus 2 squared here. And we need to multiply this by m plus 3 to get that LCD. And whatever we do to the numerator, we have to do to the denominator. Now looking at the second expression here, we have 3 over m plus 3 times n minus 2. But again, we need two factors of n minus 2. So we're going to multiply the top and bottom by that extra factor of n minus 2. Doing so, we're going to end up with 2 times m plus 3 because we're multiplying straight across over the desired LCD. Similarly, for the second expression, this 3 is multiplying n minus 2, and we're going to have our LCD. All right, so now we can go ahead and add these guys together since they have a common denominator. In the same step, though, I'm also going to distribute. So we have 2 is multiplying n plus 3, so it's going to multiply everything in our parentheses, and 3 is multiplying everything in the parentheses here. So we're going to have 2 times m, which gives me 2m, plus 2 times 3, which gives me 6. Then I'm going to end up with 3 times m minus 6. And since we have a common denominator here, I'm going to write everything over that LCD. Okay, so I kind of combined the step where I distribute this and write it over one common denominator from here to here. Now what we can do is combine like terms. I have a 2m and a 5 or 3m, so that'll give me 5m. And then I have a plus 6 and a minus 6. So our numerator is just going to end up being 5m. In the denominator here, we're still going to have this LCD. And notice we can't simplify any further. This is going to be our final answer since it's written in its lowest terms. So the sum of our original rational expressions up here is going to be 5m over the LCD that we found. All right, so that'll be it for this video.